Welcome back, statics fans. So, as promised, here's a example of a space truss that I'm going to work through with you. So, the green straight lines are the members that actually make up the truss. So, you have 3 in the basal plane from A to B, from B to D, and A to D. And then you have, from each of those points, you have 3 members going up to point C. So, you have 6 members, and you have 4 joints, and yeah, so that's all in green. The numbers associated with the arrows, those curved arrows pointing at them, are the dimensions of those particular members. And then you have forces at each point. The applied force, the only applied force, is at point D, and that's given here. We're given what the applied force is. We're asked to find the reaction forces at A, B, and C. There's 2 reaction forces at A, 1 at B, 3 at Z. All right, so first thing I'm going to do, and as always, there's multiple ways to attack these problems. Here's one of many possible solutions. So, sum of the moments about C is equal to 0. All right, so I'm going to use cross products. All right, so sum of the moments about C means that all the C forces, FCX, FCY, FCZ, are not going to come into the mix because they pass through point C, so they have no moment arm, so their moment is 0. So we're dealing with the other 1, 2, 3, 4 forces, the 2 at A, the 1 at B, and the 1 at D. All right, so that's the sum. Those are the forces we're dealing with. So let's write that out. Got to be a lot more careful in 3D about making sure we don't make just bookkeeping mistakes. So can't leave things to memory. R cross F for each of these. RCA cross FAX. So let's see, RAC. So FAX and FAY both go through point A, a position vector to the line of action of the force from the point about which you're taking the moments, point C. For both FAY and FAX is the position vector CA, from C to A. Okay, so we can use that for both of them. So RAC again, or CA again, crossed with the Y component of the reaction at A. The next force I'm going to look at is the applied force F. And that position vector we know as CD. Okay, we have dimensions for everything, so we can find these position vectors. This is tedious, but it's not a problem. RCD crossed with F, and the last one is force BX, and that's CB, going from point C to point B, position vector, crossed with F, B in the X direction. And that whole thing has to equal 0. Okay, so let's write down those position vectors. I'm going to bracket each cross product to put the position vector in. So the position vector RCA is 3I minus 12K. Okay, so going from C to A, we're going on the Z-axis. We know that this is 12. So that's 12 in the Z direction. And we know that it's 3 in the I direction. Okay, so cross that with f ax I. Actually, that's redundant, right? Because I took the unit vector out there. So fax there is a magnitude. All right, plus 3I minus 12k, same unit vector. We showed that last time up here. And that gets crossed with fay j hat. And then plus unit vector cd. Now this one's a three-dimensional unit vector. So it comes out 3 units in the x direction. It goes over 4 units in the positive j direction. And it goes downward from C to D 12 units in the k direction. That gets crossed with the applied force, which is 100I minus 100k. And we're not done yet. Plus the last force, the fbx. So its unit vector is 4j minus 12k crossed with fbx I hat. And that whole mess equals 0. Okay, now I'm not going to do every single cross product on this video, or it's going to be really long. I did them out. Here's what I ended up with for components. All right, so I'll do this intermediate step and you can check me. These are all the components I ended up getting. Minus 12 fax j hat plus 3 fay k plus 12 fay I plus 300 j minus 400 k minus 400 I minus 1200 j minus 4 fbx k minus 12 fbx j. That whole thing equals 0. Those are all the components I got after taking those 4 cross products in the moment summation up here. All right, now what you do with that mess is you make 3 equations out of it. You're going to do an I. You're going to gather the I, the j, and the k components. Each of those together. So you've got 12 fay minus 400. All right, so let me highlight those. So the I components here and here. That's it, just those 2. All right, that's going to equal 0. So this gives us fay. Nice. Okay, we know it's in the j direction, so vectorially 33.3 j. I mean, that's the subscript we gave. It was ay, so we know that that magnitude is in the j direction. Okay, j components. One here, and one here, and one here. So we've got 4 j components. We've got minus 12 fax plus 300 minus 1200 minus 12 FBX. Okay, that's got to equal 0. So when you do that out, you end up with FAX plus FBX equal to minus 75. All right, so we have one equation, two unknowns. Can't do anything with that at this point. Just let it sit there. Okay, we're going to do our K's now, which is everything that's left. So we have 3 FAY here, the minus 400, and the minus 4 FBX. So 3 FAY minus 400 minus 4 FBX equals 0. Now, we know this from up here. All right, so we can pop that in, and when you do, you get FBX equal to a negative 75. We know that now that we know this, we can put this in here, and lo and behold, FAX must equal 0. All right, so let's so we've got those guys. We've got those three forces. Very nice. All right. Next, we're going to look at the reactions at C. Okay, next. Reactions at point C. Okay, so here we're going to do sum of the forces to figure this one out. Sum of the forces in the X equals 0. So the forces in the X direction are FCX, FBX, and 100 from the applied force, right here. Okay, so, but we know, oh, and this has to equal 0. But we know FBX equals minus 75. We already found that. So we can put that in here, and we get the component of force in the X direction at C equal to a minus 25. Sum of the forces in the Y direction is 0. In the Y direction, it's FCY plus FAY equals 0. So again, FAY we found earlier on, we found that to be 33.3 from our last adventure. That goes in here. So FCY must equal a negative 33.3. And finish this up by summing the forces in the Z direction, setting them equal to 0. We only have 2 here. CZ minus 100 equals 0. So FCZ equals 100. Right. So the total reaction force at C can be written as minus 25I minus 33.3 J plus 100 K pounds. Alrighty, so now, next, going back up to the diagram. Next, what we're going to try to do is find the forces in members AB and AC. AC. Here. Okay? I'm going to erase that so it doesn't stay on there. Oops. No. There. Okay, good. All right. Now, all right, we're going to use method of sections here. So, to find the force in members AD and AC. All right, so to do this, we're going to make a cut. Parallel to the XZ plane. All right, and so that means the section of interest will look like this. All right, so we're going to have a line from D. We're going to have a line connecting D and B. And then we're going to have a bunch of segments. We're going to have one coming up that way, that way, that way, that way. Okay, so this is B here. This is D. All right, so let's orient ourselves. So we've got, whoa, that's not what I wanted. Here, here. Okay. Right there, this guy right here is F, B, X. And we know that to be equal to minus 75. And these are all in pounds. Okay, I'm not writing the units, just to avoid more clutter. Right here. All right, this one is FBC. Down here, FBA. Here. FDC. And here. FDA. Okay, those are the forces in the members that have been cut through. And let us not forget our applied force. Okay, this is F, and we know F. 100 I minus 100 K. Okay, this is our section. We cut through it. We cut through the piece, and we replaced the whole rest of the structure with equivalent forces. All right, so we need to find some unit vectors because we have to express these forces as vectors. So we're going to find a bunch of unit vectors. Unit vector in a direction DC is the vector DC over the magnitude of DC is minus 3I minus 4J plus 12K over the magnitude of that, which is 13. And that comes out to well, let's just do the whole thing. The force FDC is going to equal the magnitude F force DC times the unit vector, which doesn't get much simpler. Minus 3 over 13I minus 4 over 13J plus 12/13 K. Unit vector in the direction dA, same deal. Vector dA over the magnitude of the vector dA. All right, now dA is a bit simpler. That's just a minus 4J over 4. So that's just a minus J. So the force dA is minus the magnitude FDA J. All right. So those are unit vectors for these two guys over here. So now if we sum the moments about B here, we eliminate forces BA and BF. All right, so let's do that. Sum of the moments about B is going to equal 0. So the only forces that are creating moments are FDC, FDA, and F, the applied force. So let's sum those up. Position vector for BD. We're going to use position vector BD. Remember, anything that goes from the point about which you're taking the moment to the line of force will work. The cross product will work it out. Crossed with F dA plus R BD crossed with the applied force F plus R BD. We can use the same one because they both go through that point. And that's crossed with force DC. Okay, so this is nice because we can use the same position vector for all 3 points. All right, so when we put that in, that position vector is easy too. RBD is right along the x-axis, so that's just 3I. So this breaks down when you put some numbers in to 3I crossed with FDA, which we found to be minus F, the magnitude FDJ, plus 3I again, crossed with the applied force, 100I minus 100K, plus same position vector, crossed with, there's a bit more to this one, minus 3 over 13I minus 4 over 13J plus 12 over 13K. That whole thing equals 0. Do the cross products. And just like last time, I'll give you the components I get. I leave the cross products to you to work out. You get minus 3FDA K plus 300J minus 12 thirteenths FDCK minus 36 over 13 FDCJ, and that whole mess equals 0. Okay, again, break this into equations, and note you just have two here. You just have the J and the K. There's no I components. So, we have our J components, and we've got two of them. 300 minus 36 over 13 FDC equals 0. So that means the magnitude of force FDC equals 108.3 pounds. And the positive means it's in tension. Because as drawn. Okay. K is minus 3 times the magnitude of the force, dA. Oh, no, the K doesn't go in there. Minus 12 thirteenths FDC equals 0. You work that out because we have FDC. So you get FDA equal to minus 33.3 pounds. And this is compression as drawn. Okay, so next we're going to find AB, BC, and BD using method of joints. So joint B right here, we've got B or F BX, which we know to be minus 75 coming in this way. You've got FBC, we have F sorry about that. Okay, let's try that again. We've got that was FBC there. Okay, we have FBA and we have FBD. So this is FBD and FBA. All right. And as a reminder, this is point B. All right, so we're going to put our forces in vector notation. Which means taking or finding some unit vectors. All right, so unit vector BD is F BD over the magnitude of F BD, 3I over 3I. So F, vector FBD, we can write as the magnitude of force FBD, I. Unit vector BA, F, the force BA over the magnitude of the force BA, gives 3I minus 4J over 5. So the force BA is the magnitude of the force BA times that unit vector 3/5 I minus 4/5 J. And then the unit vector BC, force BC over magnitude BC minus 4J plus 12K over square root of 160. And that ends up giving us the vector, the force in vector form of BC equaling the magnitude times this unit vector up here, minus 4 over square root 160 J plus 12 over 1 square root 160 K. Okay, so we have all our forces in vector form. So now we're going to do a force summation. So the sum of the forces at B in each direction must equal 0. So we're going to go through each direction. In the I direction, I'm taking all the I components from all of the forces that intersect at that point. All those forces must sum to 0 in each direction. So I have minus 75 plus FBD plus 3/5 FBA all equals 0. In the J direction, I have minus 4/5 FBA minus 4 over square root 160 FBC, that equals 0. And in the K direction, I have 12 over square root 160 FBC is equal to 0. Okay, so this is nice. That tells us immediately FBC equals 0. So you put this in here, and that gives FBA equal to 0. That's got to be 0 also. And then you put that up here, and that then gives us, when you do the math there, FBD equals 75. All right, almost done. Lastly, joint A. Okay, A So we got a bunch of forces. We've been going on a while here, so I'm not going to go through all this, but when you go through all the forces, the only force that has a component, only force AC has a Z component. So there's no other force with a Z component, so the only one we hadn't found was force AC in the Z direction. That must be 0. All right, so you can logic your way through that. So I hope you see that this one is, space trusses are basically the same as the plane trusses, just trickier and a lot more detailed. All right, folks, thanks for hanging in there with me. We'll talk to you soon.